If you do so. Yeah, before you do.
Thank you very much. Hi, everybody. It's a real pleasure to be here. So I really thank the invitation. I will be talking about data quality, which I think that is a main topic into the automation of networks. And I will bring part of the work we have been doing as part of the computational data science laboratory, as it was mentioned before, but also in a new company we are creating now that is called the Tharsis, with which we develop this type of software for machine learning data analysis, but also with a main focus on interpretability, which is my main goal. Okay, so let me give a little bit of context of the topic. So I'm discussing today autonomous networks, where the goal is to minimize the role of the human into the decisions of monitoring, deploying, etc., within the network. And if you look at the vision of the industry, for instance, the DM Forum, basically this is very similar to what you get from an autonomous car. So you have different levels of autonomy, from completely manual deployment and monitoring and service providing to completely autonomous at level 5. Which in principle is associated to the idea of artificial intelligence, some sort of automation based on new technologies. Now, this has a clear analogy with the autonomous car. So people is exciting with this because they see this parallel. And in the case of the autonomous car, we have the same type of levels. So basically, you can see level 3 is essentially when the car is driving by itself, but requires some sort of human monitoring on top of it. So the humans should take charge in case that the car decides to do something funny. But then if we go to 4 and 5, it's full automation. So the person can be basically almost sleeping. And now we can take a look at the predictions that we had back 7 years, 2018. And if you see the predictions were that by last year, in 2024, sorry, I'm going to use my manual pointer, which is autonomous. Well, it needs a little bit of me. So by last year, we should have almost 3/4 of the manufacturers with level 3, which is a very high profile of automation, but it still requires a human. And then 1/4 will be essentially autonomous at some of the 2 last levels. Now, if we look at reality, what we have today is this. Even Tesla is not level, okay? And deployments are allowed in some specific regions of the country, of the world, sorry, for some specific manufacturers which are advanced at level 3. So it still requires some sort of human supervision. So I think that the message here is, okay, this analogy is very interesting for automation, but sometimes it's creating false expectations, I will say. Okay, we have seen today some ideas about automation that are quite practical, but are not totally relying on completely AI-based automation, which is something that we don't know if it's going to happen yet. We have a lot of promises. We don't know if it's going to happen. Another analogy that is very useful for autonomous network is the industrial analogy, okay, the closed loop. I think many of us have been listening to this closed loop. It comes from the industry, from the process industry, in which we have millions or billions of those that are controlling the levels of different variables. So it could be temperature variables or pHs or stuff like this. Or, I don't know, viscosity in the petrochemical industry. So basically, this is a control loop in which you have the part of the process that you want to control, and then you have a sensor associated to the variable that you want to control. And then you compare the reading of the sensor with the set point, which is our ideal value, okay? And maybe you do some sort of optimization in order to get your set point, or it's a manual thing that the engineers know because of their experience. Okay, then we put the difference of these two into the controller, and it actuates over the process with an actuator. Now, this is for a single variable. So a variable like a temperature, with which or to which you have full observability. So you are really reading the variable and you know what is the value. But if you escalate this to more complex stuff, then the analogy breaks down a little bit. So this is the analogy we want to make, or sometimes some people is thinking that we want to make in autonomous networks, where we have the complete network and we are going to do some kind of sensing, maybe using modern technology like telemetry. And then this telemetry is going to be compared to maybe some intent that we have defined for the network. And there will be a controller which is capable of interpreting this intent-based approach, which maybe has some sort of natural language processing, or maybe we have made a format that is easy to interpret and then compare with reality. And by some sort of actuation, we come back to the network. Now, complexity here is much, much higher. So again, the analogy can be useful, but we need to understand the difficulties, the challenges that are on top of this. Also, one thing that is especially different is that we don't have the full observability of the network. This is something that we know for sure, because we cannot use all the resources in the network to observe everything in it. So this is very challenging because this telemetry is not going to be perfect, meaning that the comparison between these two is also uncertain. And working with uncertainty is something that AI doesn't do that well because we need to train it, and the quality of the data, which is my main topic today, it's very much the quality of the machine learning tool that we are going to use. Also, I think that we should take care that this analogy should have a human somewhere. Doesn't mean that it has to be a low level. We can automatize a lot of stuff, but there has to be a human somewhere to double check some of the decisions that we make. Now, an analogy that I do think that is very interesting, well, I do think that the other two are, but they can be also confusing. An analogy that I would like to reflect on today is the one that we use when we are developing a machine learning model on a manual basis. So I get in my computer, I get some data, I do some training, and I assess the performance of the model. So basically, these are a number of the steps that I decided to put here, which are according to my experience, and of course, it's my own experience. So first of all, we need to have some clear problem definition, okay? And this again depends on the intent-based technology, because we want to automatize everything. So even deploy of a new service means a new problem definition that we need to automatically identify. So it's not that really easy, but it can be done. Then we need to recollect the data, and that means several decisions. I put some here. So for instance, where do I put the sensors? So I'm sensing traffic. Where do I put my sensors? Where do I take the measurements and store them? And then the strategy I will be talking about later though. Then I will need to go through a data preprocessing step with some potential feature and observation engineering. Some models have the ability to incorporate this inside the model, some others not. So probably we will need it, especially the observation engineering. I don't think there is any model that does it. But anyways, there might be some preprocessing to do, and then there might be some data cleaning, some data selection that we need to do, like taking outliers outside or whatever it is, okay? Then comes labeling. And labeling, extremely hard to automatize. Actually, this is the main problem I think we have been facing in the last years. And people will think that in unsupervised cases, you don't have labeling, but you do. You need to identify what is the normal traffic or the normal observations and identify which are anomalous to get rid of them when you are training your model. So labeling is all over the place, and labeling is really complicated to automatize. Think about it. Sometimes we are developing models that require millions of items of data. We need a labeling for that, okay? So how do we do this? If we do it manually, 1 million, it's very time consuming. So when we get the model, it's going to be outdated because traffic changes, and these are dynamic services, so they change, okay? So it's quite complicated. People is doing research on this, and I think we can solve it at some point, but I don't think we're there yet. Then
Of course, we need to do model training. And one thing we need to decide is the model choice. And one thing I would like to convince you is that deep learning is not the only thing that we can do. Actually, we don't need deep learning for many cases. I think there are cases in which we really need that because we have the data for that, and we also have the complexity for that. Well, there are other cases that we don't, okay? Somebody, I think it was Remy, commented before, I didn't do any artificial intelligence for solving this problem. And I agree with this view, right? If you don't need it, why bother? Then we do some parameter optimization. We know how to do this. And then we do some performance evaluation, which has to be with independent data, so numerical approach, maybe there's double validation, SD validation, whatever it is. But at the end, we need to know that the model is working fine. Otherwise, you wouldn't put the model to drive your car, correct? So maybe we need to go back this step again and again until we get to something that we really like. And then after this, we can deploy it. And then comes the second problem, which is monitoring. And, the models get outdated, so we need to retrieve new data to update the model and maintain it. Right, so this is the manual pipeline. I think reflecting on the manual pipeline is super important for us. Why? Because if we want to go to the automatic pipeline, we need to reflect on all these steps. And I think, well, okay, I'm going to say a random number, but people do this and nobody complains, okay? I think that 99 of the people in the research community, let's say, is only working on this. It is not really useful for us because we have a lot to solve for the future. Yeah, so this, for instance, sensor placement. Okay, the code is connected to what we know today, maybe. Okay, that's my view again. So if you see green, is that probably we know how to do it with the current knowledge. If you see yellow, oranges, okay, we are close to there. If you see the dark orange or reddish, it means that we are very far because probably people is not doing research on this. So let me focus on the orangey ones. So we have the strategy. Where do we get the data from? Is our own data? So do we have the right to use it? And if so, is the practicalities of the service that I want to deploy really meeting the needs of data that I have? So I have to retrieve 1 million observations. Do I have the time? Can I put my AI there, reading data until it gets working properly? So these are things we need to reflect, okay? Then there is data selection, and by data selection, I mean, we have seen in many situations that doing some proper identification of outliers or getting rid of some part of my data or checking, I don't know, several things like data cleaning and stuff similar, we get a very large advantage in performance. So this is very easy to do it on a manual level because I have visualizations and I can more or less know how to do it. But on an automatic level, it's not that easy, I think. Or at least I don't see so much research on it. Then data labeling, there is people doing research on this, but it's recent research. It's the last 5 years, I would say there are many papers realizing about this problem and many people working on it. So that's pretty good. Then there is the model choice. I think there are some popular solutions based on deep learning, and maybe we need to expand a little bit our ideas. And then finally, this part, which I won't be talking about. So I will concentrate the rest of my talk in this part, and I'm going to go backwards because of convenience for this plan. So model choice. I would like to convince you today that the model choice is a trade-off. At least a trade-off between accuracy and interpretability. And why so? Most people is looking at accuracy alone. And accuracy alone can be deceiving. And this is because we don't have a full observability of the accuracy. The accuracy is based on labeling, which is uncertain by itself. So measuring accuracy is complicated. And also, there are some constraints that make accuracy not the only relevant. Why interpretability matters? Well, there are many situations, and we need to think that we are building also cybersecurity is just one example of this autonomous network, not just, it's probably the most important one. but it's it's included into this idea of autonomous networks. And there is compliance to do, okay? There are some audits that we will need to show when we are putting something that is an automatic agent on top of a very important service in a very important infrastructure. We will probably need to show that the agent is ready for that, or we will have to face the legal consequences. So it's better that we start working on that now. Now, also, when we are creating the new model, technicians, so people that is working in Google on LLMs and Google or AI or any AI company is also trying to interpret the models. Believe it or not, they need to interpret them because they need to know how they work to some point of that. Okay, so that's you achieve it through interpretation, and there are several of the learning technologies that are improving very much on interpretation. Now, another thing is the why. Why did I flag this issue like an anomaly or a attack or a malicious activity, whatever it is? We need to have a response from the models to clarify why they arrived to this conclusion, okay? And one reason for this is that we can really minimize false positives and negatives if we have the double layer. So we have the model and then we have the interpretability layer, if you like, or a model that can be interpreted by itself. Because at least in my experience, it's very useful if you have an interpretation that the model said that this is an anomaly, then you take maybe 1 second to disregard this anomaly as a false positive because you can interpret it. So that's pretty simple, pretty easy, and it's really convenient for a cybersecurity pipeline. There is always a cybersecurity analyst doing some sort of forensics. And if he has a clear picture of why the model was the victim as an attack, we can say, okay, that's not really an attack. Let's move to the next one, right? So interpretability is very important because false positives and negatives exist. If you see this performance of 100% in some papers, you can doubt a little bit about that. Then, of course, for compliance, I was saying before, but we need to prove that our models are not biased according to geography, according to service level, whatever it is. So they have to be fair and robust. And finally, if we need to go to court, we need something to show, right? So this is chain of custody. There is another very powerful reason. This is an editorial in Nature Machine Intelligence that of the past month. And they make the emphasis on what is the data that we are using. We need to have the copyright of the data. We need to create a model. This is uncertain today, but there is going to be a law in the future, very clear regulation, and we will need to take this also into account. So we cannot just pick any random data we like, except for Google, they can, or some other companies as well. But in principle, we cannot do that. So we really need to understand what is the data that we have at our disposal. Okay. In the literature, you see two main trends for interpretability. One trend is trying to explain deep learning models, black box models in particular. And this is often called explainable artificial intelligence. And there is another trend, believe it or not, that is using white box AI models and then interpret them directly. And these two trends are not that separated in the scientific literature. So for instance, let me give you one example. This is people from my university. This is my faculty is really, it has several very good scientists that are kind of top. And this is, I think, the highest cited paper in explainable AI. So many people looking into this idea. Deep learning and trying to identify what is happening. This is the proposal that they make. And you can see that it's quite challenging, okay? Because these models are quite big and it makes sense. We are talking about models from billions, well, from millions to billions of parameters that we need to interpret. And that is challenging, okay? They divide this exploratory artificial intelligence or explanatory, sorry, in three sections, which I really like. The first one is about data explainability, meaning before I train my model, I want to understand the data. because the data may have outliers or several clusters or something, okay? So it's natural that we go and look the data before we use it for training. This is the natural pipeline. This is what most scientists do in AI. It's very important to look into your data before you train anything, okay? Sometimes it's complicated because your data can be massive, but you can do tricks. You can take statistics and show stuff. So these are the techniques based on data explainability. Then we have the model explainability, which is itself trying to understand how I said before, okay? How the data is being encapsulated into the model up to a classification step. And finally, there is the post-hoc explainability, which is trying to give you an answer to the why this was detected as an anomaly or as an attack. I think this is quite nice, this separation in 3 steps. Then there is the other view. So this paper got really popular as well. So you can see that there is many people looking at this direction. Stop explaining black box machine learning models for high stakes decisions, use interpretable models instead. High stakes decision is exactly what we do in network. Okay, but yeah, okay, two ways to look into the same problem. And this is the type of models that you get and that you can interpret in the core. And again, the more parameters that you have, because your service or whatever you have is more challenging, the more complicated the interpretation gets, but this happens for the both strategies, okay? So in my lab and in the company, what we try to do is to use a technology that is called multivariate analysis for interpretation. And I'm not going to lie to you, it's complicated to interpret when data is massive as well. But there are some good approaches to identify the, let's say, distribution of my observations and see how they move according to some classification that I want to do. So classification would be in the colors. And then I can associate these movements, this cluster, these features in the observational space with the variables that are the features that I'm using in my data set. So if you're interested in this idea, this is part of a recent paper in which we try to come up with some feature learning ability, which retains interpretability as well. And we can also use this for black box interpretability. So for instance, you have here a big neural network. It's 10 years old, this one, because this is very time consuming. And you can see that this network is having a very high accuracy classification of 5 classes. This is photographs in this case. It's not networking, but it's just a case study. And we can derive these kind of plots, multivariate plots for interpretation, and we can identify which parts of the network are the most useful in my classification, maybe reduce it, compress it, or just try to give some meaning of this amount of parameters. Here you have 6 million parameters. It's possible to probably go one by one and understand what they are doing, but we can get a general picture of how it is working to some extent. Now, the second thing I wanted to talk about, and I don't know if I'm running out of time, might be the case. I'm already out of time?
You have 7 minutes.
7 minutes is fine. Okay. So the second thing was data selection. So improve data quality through data selection. This is the main idea connected to data quality. Here, very briefly, we did this experiment in which we wanted to see what is the effect of doing some different selections in our calibration data. And this was with a real capture of 4 months of traffic in one of the biggest clouds in Spain. And what we did was the following. So this is what we use for calibration data, the first 3 months, and then the last month was the validation data, the test data, whatever you call it. And in this part, we also induced some artificial attacks. And we label the data according to these artificial attacks. So we have, in principle, we have a very, let's say, objective labeling, but that is not true because actually there are attacks. You can see these red ones here all over the place in what I said as normal data. So this is a challenge at the end. Now, on a summary of this result, you can take a look at the paper if you like. But what we found is that the best performing models depended, sorry, I think it's this one depended more on the data that I was using than on the machine learning model that I was trying to use. So in this case study, I'm not saying that this is general, and I don't think it is, okay? But in this case study, it's more important the data that I use for training than the machine learning model that I'm using. And again, how many presentations have you seen about improving the quality of the data rather than trying a new classifier or a new model algorithm, whatever it is? Also, we found that there were many errors in the labeling, false negatives and false positives. So this means another thing that is even more important, in my opinion, than the previous one, is that even our performance evaluation is uncertain. So even my observation that this is the best model might be wrong because my labeling is not correct. So a lot to think about, okay? Right, and to end this presentation, I just wanted to touch about data strategy. So for me, data strategy is how do I fit my model in a real situation. So I wanna learn, I wanna put an anomaly detector or whatever it is into a service, and I need to train it there because the data is gonna be particular there. So how do I do that, okay? Where do I take the data from? There are many approaches, but maybe these three are like the most radical ones. So I can train it completely into the loop. So I put it there and start from scratch, and then I train it with my own data. Then I can do model transfer, which is very cool. So I kind of pre-train a model with a lot of data. So maybe a foundational model, or maybe I do it with another network and I want to translate my service to another network. This can work, but I still need some data to retrain, of course, to do this transfer. Or I can do selective experiments, which is not always possible because sometimes I cannot really move my service to certain situations because the performance is going to be really affected. Here you have some papers about this last trend, so model transfer idea, which I think is reasonable, but has some practicalities that we need to solve. So for instance, I find particularly interesting this one. So we can generate a generative model for network traffic dynamics. Yeah, I think we can. It's the same idea as with the images, right? But generative models, well, the foundational models, what they do is essentially to understand the most general features in this type of data. And then we can transfer it to our service and use this idea. But it requires a lot of data. So yeah, this is the design of experiment. We have been doing some research on this, but I won't touch it because I don't have that science. So if you compare all these situations, then there are several things you need to realize if you want to go for one or the other. In the case of local data, this is going to require a lot of data, but information is going to be poor. So basically, you need to find the needle in the haystack, okay? And it's easy to automatize, that is true. But the problem is, do I have this training process available so I can put that in my service and wait until it gets better? That's very challenging, in my opinion. The model transfer is better in that regard, but then you need a model pre-trained, and a model pre-trained on a relevant database, not on any database that we simulate. That is not really working, okay? So if we want to do it, we need to reflect a little bit on this. And this is maybe easier in terms of amount of information that I need to do, but it's not always possible to do it in our service. So just to give a number of conclusions on this talk, and this is again my view of all the problem. We need to be aware of analogies. Analogies are useful, but they can also be deceiving, so don't get deceived by them. We need to study the challenges, so we probably need more people looking at those challenges or at least some of the ones that I was discussing. I think we need to look at the future at some person on the loop at some level. Okay, so we don't really need to do research today about optimizing everything. So maybe try to reflect on something that is more practical today, maybe. The model that we are going to use, we don't really need deep learning in all the cases, so maybe we need to double check about the accuracy and interpretability and think more about this interpretability, what is providing. In cybersecurity, we really need interpretability, and most people don't think about this. I do think we need it. Data is also a matter of availability. Do I have in my practical example that I'm doing in this research, do I really have this data available, or do I have this foundational model available? Can I fit a new foundational model? That's not for everybody, okay? And then the access to the relevant data is not for everybody. So only, I would say, big companies and really huge universities can do this properly. So I don't know. And finally, I think data quality, we need to realize that it's in the core of everything. So we need to do more research about how to improve it on an automatic basis.
Well, thank you so much. Thank you.
Any questions in the room? Yes, you do. Yeah, I have a question. Thank you for your presentation. Very interesting. I had a question about the closed loop diagram at the beginning of the presentation.
Yeah.
This presentation was focused about the telemetry data. But it seems in your diagram that you combine intent with IBM and telemetry data in your ML model. How does it work?
No, this is only an instruction on how we can make this analogy. Because to me, intent-based networking is very much like putting a set point in an industry. Okay? But I'm not saying that we have done this, not at all.
Okay.
I'm just trying to see, okay, if this is the analogy we are going to make, how I can translate all these blocks into something people is working on in networking today.
So maybe a follow-up question. Here, since the network is going to change something, the switch, the routers, or whatever, it is also going to change the traffic.
Yeah.
And the traffic is your data.
Yeah.
So instead of improving the accuracy of whatever model you are using, you could be focusing on improving the quality of the data generated by the network.
Yeah. Yeah. I mean, that might be working for some specific goals, but maybe not for others. So it depends very much, right?
Well, since you made the parallel with the self-driving car, the big problem with self-driving car is the human conductors.
Yeah.
If everything was automatic, it would be very easy.
Yeah.
So here, I don't quite see the parallel in networking because you want to follow a protocol, and protocol is managed by the router. So there is much less human driven characteristics for the traffic. So that means that the loop is much more important.
Yeah. Well, I think the analogy is again a little bit fake in some details, but then again, you have also, even if all the cars were automatic, which could be like trains, right? And yeah, I don't know. But see, even in this situation, you still will have pedestrians and traffic lights, or I don't know, for instance, traffic light goes off, but especially pedestrians. And then the traffic in the network, part of it is going to be also generated by humans. So again, there is some things that you cannot really predict, and you need to be robust. And
for human behavior and comfort, there has been a lot of studies that show that humans are quite predictable, actually.
yeah,
They follow some pattern of usage, etc. So there is less unpredictability from the human side in the networks.
yeah, no, I agree on that. But maybe with the future services and the amount of traffic and the automation of I put this service, I deploy this service, and I take it out, and this type of visualization of the future network, I'm not sure that we are so capable of adjust at the level that is expected.
But I might be wrong. What I'm saying is that probably we shouldn't be working only on the models. So maybe we need to look at something else because, yeah, it needs to work in practice.
How we evaluate
Yeah.
the models. Here, the model has a direct impact on the future training of the model.
Yeah, yeah, exactly. That's a problem in itself. Yeah, yeah, I agree completely. Yeah.
With respect to that, so you said that, well, you said you cannot generalize about that, but one of your experiments, you have shown that the performance of the model was dependent on the quality of the training data. And we also, I mean, have worked on that point. And actually, if we want to improve evaluation, it's not a trade-off. There's a kind of balance between the training and the testing data. So for example, in your experiment, was the test data fixed?
No. In the result that I'm showing, it wasn't fixed. To be honest, I don't think that the amount of anomalies we found will change to a large extent.
Yeah.
So we still have some, but no, we didn't change it. We didn't change it. What we did, and I think is quite useful again, was to use interpretation, so visualizations and pipelines that you can interpret. And then we found this true and well, and the false negative and positives, because I think this is a layer that we really need. Yeah.
For this visualization that you have shown, what was the purpose, like trying to show separability of data?
Yeah, well, in this case was traffic from, I think it was the longest Wi-Fi capture, this one. Yeah, in Dartmouth College. Nobody had ever looked into that data. So they have a disruption in the capture for 1.5 years, and they didn't notice. That happens many times because if you don't look at the data, you don't realize. So you think this is always taken from services that are, automatic and taking data. And sometimes you realize that something went off and it's too late, right? So, yeah. Yeah.
Use of question? I had the last one about close to your conclusion where you compare the different issue with training the model. So you have, if you're training from scratch, you need like a large amount of data. And you said at that point that the information was poor. I didn't completely understand what, I mean, I have some idea, but could you?
No, what I mean maybe is the wording is not the most specific, but what I mean is that it's kind of needle in a haystack. So you need to find, you need to produce a lot of data. Most of it probably is not that necessary in order to get some picture of it.
Of the domain.
Yeah, of the domain. So that's what I meant. And I think the emphasis is in the amount of data that you need for training.
The more you have, the more you can explore the domain.
Yeah.
Thank you very much.
Thank you.